So a lot of the things that might follow a exponential growth or decay model for a time do have a place where they kind of have to cap off. And that's what we get in terms of things called logistic growth models, where we can see that we have a big exponential growth rate for a time and then it tails off and caps off in terms of a function of form f of t equals a equals c over 1 plus ae to the negative bt for constants a, b, and c that are bigger than 0 for b and c that show as t grows to infinity, as this thing tends offward, it hits a very hard horizontal asymptote that it does not go past. And one really natural application for this would be something like the spread of a virus, where it should make sense that a virus will shoot up and have a lot of new hosts. It will infect a lot of people very, very quickly. But as people get more careful, as they take more precautions, as they are more and more safe, less and less people will get infected, or failing that,
I feel threatened!
Eventually everyone just gets sick, at which point there are no more hosts. And so the virus can't spread anymore. But because I'm sure all of you guys are kind of sick of hearing about viruses, at least for a little while, I'm not going to do that model in here. We're going to look at something else. For our example here, we have that psychologists believe the model f of t equals 0.8 over 1 plus e to the negative 0.2t describes the proportion of correct responses f of t after t learning trials. Find the proportion of correct responses prior to learning trials taking place, then find the proportion of correct responses after 15 trials, and describe the limiting size for the proportions as you take more and more trials. So that is, our ultimate goal here is going to be to describe something like an asymptote. So if we're looking for the initial value first, that means we are looking for what happens before any trials take place. So we're looking to find what happens when t equals 0. And from our model here, it's just a matter of plugging and chugging. Nothing too subtle to be done in this case. F of 0 ends up being 0.8 over 1 plus e to the negative 0.2 times 0. So in this case, to be sure, we have that c is equal to 0.8, a is equal to 1, and b is equal to 0.2. And this is the very clear value, right? It's perfect. Well, no, you actually want a proportion. And actually, in this case, it's not quite as bad as it might look initially, because here we're raising an e to the 0. Anything raised to the 0, no matter how nasty it might look there, is just 1. So we have 0.8 over 1 plus 1, or 0.8 over 2, or 0.4, which is to say that we would expect about 40% of the responses to be correct without any training taking place. It's just below a 50-50 shot, which that might make sense, right? You might get about half of them right just by guessing, depending on what kind of trials it is we're talking about here. I'm assuming it's multiple choice, but I don't actually know. Anyway, that's what we get for 0. So if we instead take 15 trials, we take t equals 15, well, then we're going to be looking at f of 15, which would mean looking at c, 0.8 over 1 plus ae, so 1e, raised to the negative, what is that one called again? b, 0.2 times 15, which unfortunately isn't quite as clean. There, up to my shaky line, I don't know what happened with that. We would have 0.8 over 1 plus e to the negative 3. That's what you get is negative 3. Where, again, you can't just get a nice even number there, unfortunately, but we'll round that off and say that the value there is about 76%. It's 0.76 rounded to the nearest percent, where that would mean that you get about 76% of the answers correct, assuming you're taking 15 trials. You're trying out your learning for 15 times of whatever a learning trial is according to these psychologists. And then if we want to find out what we're expecting the cap to be here, we have that since C is equal to 0.8, and that value C always defines our horizontal asymptotes, we would expect that the cap there is 80%. So no matter how many trials you take, you could take another 10 or you could take another 1,000, you would expect that the amount of correct answers sticks at 80% overall based on the model we're using. Maybe that's reasonable, maybe it isn't. It's a question of how effective learning really is for this type of situation, and I'm sure they didn't push that to the absolute breaking point there. They just fit their model to the data as best as what they had, which is actually the sort of thing that we're going to talk about to finish this chapter with in terms of how you describe a thing, a data set, using certain equations to build models.